Next chapter, simple classification of substances. Now, we talked about matter in the previous chapter. In order to study matter, we need to classify various forms of matter according to their shared physical characteristics to make it easier. Matter, whether in solid, liquid or gas, can be classified either as a mixture or as a pure substance. A mixture can either be homogeneous or heterogeneous. Pure substances, on the other hand, can be classified either as elements or compounds. By the end of this Form 1 chemistry, we should have exhausted studying each and every part of this chart. We've done matter. Now let's go to mixtures. A mixture is made up of two or more substances that are not chemically combined. Therefore, mixtures do not have specific chemical properties. Their properties depend on the substances or components that make them. The component of a mixture can be extracted using appropriate separation methods. Depending on their appearances, mixtures can be heterogeneous or homogeneous. The components of some heterogeneous mixtures can be distinguished with the naked eye and are not evenly distributed. The components of some heterogeneous mixtures can only be distinguished using a microscope. This is the case with colloids. The components of a homogeneous mixture or solution are evenly distributed, and so they cannot be distinguished, not even with the microscope. Depending on the state of the components, mixtures can be grouped as solid-solid mixtures, for example, iron filings and sulfur. Solid-liquid mixtures, for example, sugar in water solution. Liquid-liquid mixtures, for example, alcohol and water. Liquid gas mixtures, for example, carbon dioxide mixed with water. And gas-gas mixtures, for example, air, which is a mixture of several gases. A large part of studying matter requires substances in their pure form, and yet matter exists in nature, mostly as mixtures. Fortunately, scientists have devised various methods of separation of the components of these mixtures. Each method is appropriate for a certain kind of a mixture. These methods include use of magnets, decantation, evaporation, filtration, separating funnel, sublimation, crystallization, distillation, and chromatography, among many others. Traditional methods of separation include hand picking, sieving, and winnowing. Hand picking is used for separating the components of a mixture which are different in color, size, and shape. For example, cereals and pebbles. Sieving is a method used for separating solids when the constituents of the mixture are of different sizes. Winnowing is generally used to separate grain from husk after threshing. This method is based on differences in weight of the components of the mixture. The lighter components are blown away by the wind. Use of magnets. This method is applied in separation of components of a mixture in which one component is magnetic and the other is not. For example, a mixture of iron filings and sulfur. The magnet will attract the iron filings, leaving the sulfur powder behind. Next method is sublimation. This is a method of separating a solid-solid mixture in which one of the components undergoes sublimation, That is, it transits from solid to vapor directly. For example, separating ammonium chloride from salt. We put the mixture in a china dish and cover it with a funnel. We block the tip of the funnel with a cotton wool. The china dish is heated gently. Ammonium chloride, a sublimate substance, changes into vapor and condenses on the cooler parts of the funnel. The non-sublimate substance, sand, will remain behind in the china dish. The ammonium chloride is then scrapped from the inner side of the funnel, and hence the mixture is separated. Other sublimate solids include naphthalene, iodine, camphor, and benzoic acid. Solid-liquid mixtures. We start with sedimentation and decantation. This method is used to separate a solid-liquid mixture in which the solid is not soluble in the liquid, like water and sand. The mixture is allowed to stand for some time undisturbed. You will see that the sand particles settle down at the bottom of the container, forming sediments. This process of settling down of heavier insoluble particles from the mixture is called sedimentation. The clear water above the sediment is then gently poured into another beaker, leaving the sand behind. This process of transferring the clear liquid is called decantation. Filtration is a more efficient method of separating an insoluble solid from a liquid like sand and water. We take a filter paper and fold it into half to make a cone like this one. We place the cone in a funnel fixed on a stand. We pour the sand-water mixture through the filter paper. The sand particles get trapped by the filter paper while the clear water sieves through and is collected in another beaker below the funnel. The clear water collected is called the filtrate, while the solid that is left on the filter paper is called the residue. This method is called filtration. One disadvantage is that it is a slow process. Evaporation is a separation method used to obtain a soluble solid from a solution, like obtaining salt from a salt solution. We take a solution of salt and water in a dish and heat it gently. You will see that the water evaporates, leaving behind the salt as a white solid. Evaporation is used to separate non-volatile soluble solids from its volatile liquid solvent. One disadvantage of this method is that it is an expensive process when it's done on a large scale. Next, crystallization. This is also a method of obtaining a solid from a solution. It is a special kind of evaporation method. Crystallization is the process of separating a pure substance in the form of crystals from its hot saturated solution by cooling. For instance, sugar is added to hot water to form a syrup. The syrup is then allowed to cool. Fine particles of sugar separate from the syrup. These fine particles are called crystals, which have definite geometric shapes and are formed by natural processes. Crystallization can also be used in purification of substances. For example, we take a sample of impure copper-2 sulfate in a china dish. We dissolve this in water. We filter the copper-2 sulfate solution. Next, we evaporate the content until we get a saturated solution. Cover the solution with a filter paper and leave it at room temperature to cool for a day. After a day, pure crystals of copper-2 sulfate will be formed. The point is, the salts contain water of crystallization and must not be evaporated to dryness. Crystallization is used for purification of salt from seawater and separation of crystals of alum from impure samples. Distillation. Now, in evaporation, only the solid is obtained after separation. Distillation is a separation method for a solution in which both the solid and solvent are obtained. It is a process of heating a solution to form vapor and then condensing the vapor to form liquid. It is used to separate two or more substances in solution or for purification of water. This is the apparatus set up for distillation. Salt water in a retort is heated till the water vaporizes. The steam is collected in the beaker, which is connected to the retort by a Liebig condenser. The steam condenses into liquid water and the salt is left behind in the retort. Notice that cold water flows in the Liebig condenser in the opposite direction as the steam. This is called countercurrent flow and ensures efficient cooling. Next is separation of liquid-liquid mixtures. First method, separating funnel. Now, a separating funnel is used to separate immiscible liquids like water and oil. Immiscible liquids are usually of different densities. A separating funnel is a special flask in the shape of an inverted cone. It has a mouth at the top and a stopcock at the bottom. The mixture is put into the separating funnel, placed on a stand. It is allowed to stand for some time. The two liquids form two distinct layers, with the lighter liquid coming to the top and the denser one at the bottom. The stopcock is then opened and the bottom liquid is drained. Then the top layer is removed into another beaker, so the mixture is now separated. Miscible liquids can also be separated by distillation, provided they have a huge difference in their boiling points. For example, a mixture of water and acetone. The mixture is placed in a distillation flask. The neck tube is attached to a Liebig condenser, which is a long glass tube within a glass jacket with an inlet and an outlet for water. The mouth of the flask is fitted with a one-holed rubber cork through which a thermometer is introduced. When the mixture is heated, acetone, which has a lower boiling point, vaporizes first and then condenses in the Liebig condenser. It is collected at the condenser outlet. Water is left behind in the distillation flask. This kind of distillation is used only when the components of the mixture have huge differences in their boiling points. What if the boiling points are close? In case the difference in the boiling points is less than 25 degrees Celsius, we use fractional distillation method. Let's take an example of water and ethanol. Water boils at 100 degrees Celsius and ethanol at 78 degrees Celsius. The two liquids can be separated by fractional distillation, which is a modified kind of simple distillation. The only difference is that a fractionating column is fitted in the distillation flask and packed with porcelain chips or glass beads. The fractionating column plays the role of allowing the water vapor to condense into liquid and flow back into the distillation flask before the boiling point of water is reached. The glass beads increase the surface area for condensation. When the mixture is heated, ethanol boils out fast at 78 degrees Celsius and the vapor is condensed in the Liebig condenser and collected in the conical flask. Water is left behind in the distillation flask. Again, observe the Liebig condenser uses countercurrent flow for effective cooling and condensation. Fractional distillation is applied industrially in separation of oxygen from air in what we call fractional distillation of liquid air. The last method of separation that we look at is chromatography. Chromatography is an analytical method used to separate colored substances, especially pigments. In chromatography, the sample is distributed between two phases, a stationary and a mobile phase. In paper chromatography, the stationary phase is usually a piece of high-quality filter paper. The mobile phase is usually a developing solution that dissolves the sample and carries it up the filter paper over a certain distance. The different components of the sample mixture are carried up the paper through different distances. Thus, the components of the mixture are separated. The distance traveled by each component depends on two factors. 1. Solubility, or how well it dissolves in the solvent or the mobile phase. The more soluble the substance, the further up it moves. In this case, our sample is a mixture of 3 substances and each is carried over a certain height up the filter paper. The one that moves the farthest is the most soluble. And secondly, adsorption, or how strongly the substance is attracted to the filter paper. The stronger the adsorption, the slower it moves. And so it's really a combination of these two factors that determine how far a substance moves. So in this case, we can say that the lowest substance had the strongest adsorption or the lowest solubility. You should notice that the mixture is now separated into pure substances. The horizontal line on which the sample mixture is placed is called the baseline. So the sample is placed on the baseline. Then we place the filter paper into the solvent. The solvent level must be below the baseline. So the solvent moves up and separates the sample into various components. The farthest point reached by the solvent is called the solvent front. We then remove the filter paper and allow it to dry. Then we measure the distance from the baseline to the solvent front and also to each of the sample. From the values, we can calculate the RF values for each component. RF is equal to A over B. The RF value is important in identification of the substances. The RF value is specific for a particular substance, so you can refer to a standard table and identify the substance. Chromatography is used in 3 things. First, to find out how many substances are in the mixture. In this case, we said it's 3 because we had 3 components. Secondly, to check for purity of substances. Pure simply means it contains only one substance. So if it separates only into one spot, then it's a pure substance. Ours was not pure. And lastly, to identify the substances. So we don't just want to see the substances separate, we want to know what they are. This could be based on their RF values, or alternatively, we can run a known substance along to find whether any components move the same distance. For example, if you have two known substances A and B and an unknown substance U, you can run them simultaneously on a paper chromatography. So we have A, then we place B, and then U. We place it in a mobile phase. The solvent rises and carries the components of the sample to different heights. From this chromatogram, we can conclude that the unknown substance is actually B. Next, pure substances. Now, having looked at mixtures, their types and how they can be separated, we now look at pure substances. The thing is, when a mixture is separated into its constituent components, those individual components are now pure substances. So, copper 2 sulfate is a pure substance. Water is also a pure substance. But a solution of copper 2 sulfate in water is not a pure substance. It is a mixture. Pure substances are further classified into elements and compounds. An element is a pure substance that cannot be broken further into smaller substances by chemical means. Examples of elements include sodium, hydrogen, carbon, nitrogen, sulfur, and many others. In nature, there are over 110 known elements, and they are arranged in what we call a periodic table that we will see in Form 2. Elements are made up of atoms. An atom is defined as the smallest particle of an element that can take part in